Hello everyone. In the last video, we have done constitutional isomer. So today we are going to start the geometrical isomer. Okay. So geometrical isomer is basically present in carbon double bond carbon, and double bond carbon have restricted rotation or hindered rotation. So any carbon double bond carbon can show geometrical, but there is a condition. I said any carbon double bond carbon can show geometrical isomer, but condition is that double bonded carbon must have different connectivity, must have different connectivity. For example, look at this double bond. Suppose this carbon have one methyl and one hydrogen, and this carbon also have one methyl and one hydrogen. So now you can see both the double bonded carbon have different connectivity. So this double bond can form geometrical isomer. If any of the carbon have two same group, for example, look at this one. So this carbon have two same group, while this one have different, but any one of them have same, then it would not show geometrical. So both the carbons should have different connectivity. Do not compare like this, like both methyl is in the up, so it should be same. No. Always compare each individual carbon of the double bond have different connectivity. For example, suppose we have this compound and we have to find out which of the double bond is showing geometrical isomer. So first job is to balance this double bond. So here we have 2H. This carbon have a carbon bond, so it should have one hydrogen. And this carbon have one carbon, there is a hydrogen. This carbon have a methyl. This is the carbon having two methyl group. And here we have one H. So now you can see this carbon have two same groups, so it would not show geometrical. This carbon have two same groups, so it would not show geometrical. And this carbon have two different things. One is the hydrogen and one is a carbon, so this one is a different. And this one is also different, so it can show geometrical. Makes sense? So this is the way you can find out the geometrical isomer in double bond. So any carbon double bond carbon can form geometrical, but condition is that both the carbons should have different connectivity. And if anyone is showing geometrical, then it can form two pair of isomer. It could be cis trans or E and G. So let's talk about first cis and trans. So what is cis? When two same groups are in same side. Called as cis. You can see both methyl is in the same side, so this one is a cis form. And what is trans? When two same groups are in opposite side, called as trans. For example, Look at this double bond. Both methyl is in the anti side, so this one is a transform. Here we have 3 double bond and assign which one is cis, which one is trans. 1, 2, 3. So first we can balance with the H. Here we have 2H. Here 1. This carbon have 1H. Here 1. And here 1H. Here 1. And this one is methyl. So now you can see the first one, this carbon have 2 same connectivity, so it's not showing geometrical, so not available. Cis trans not available. In the second one, both the hydrogen are in anti side, you can see. So this one is trans, and here both the hydrogen in the same side. So this one is cis. Clear? The next is E and G. But before moving to E and G, I would like to discuss a rule which is called CIPS rule, which is also known as priority order rule. Priority rule. So the very first rule is priority is decided by atomic number. Priority is decided by atomic number. Higher the atomic number, higher the atomic number, greater the priority, greater the priority. Like this. So if you are going to assign the priority here, so iodine have the highest, then bromine, then chlorine, and then fluorine. The second rule, in case of isotopes, priority is decided by mass number. For example, suppose we have this one. Here hydrogen, here deuterium. So it is very clear hydrogen and deuterium are isotopes of each other. So hydrogen, atomic number 1, mass number 1. Deuterium, atomic number 1, mass number 2. So greater the mass number, higher the priority. So in case of isotopes, priority is decided by mass number, which means greater the mass number, higher the priority. So chlorine 1, fluorine 2, between hydrogen and deuterium, deuterium would be 3 and hydrogen would be the 4th. Now the next, if you have a group of atom, for example, suppose we have OH, NH2, CH3, suppose CH2Cl. Then what should be the priority here? So whenever we have a group of atom, always compare the very first atom in each group, always. Suppose in NH2, we have to compare the nitrogen. In OH, oxygen. So look at here. Here N, here O, here C, C. So oxygen has higher atomic number, so this bond would be 1. Then nitrogen 2. Now look at this CH2Cl and CH3. So if you look at CH3, H, 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 and in CH2Cl, carbon, then chlorine has high priority, then hydrogen, then hydrogen. So we can say, or even you can say C, H, 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 and C, Cl, H, and H, like that. So suppose carbon, carbon is same. Next is hydrogen, next is chlorine. So chlorine has more priority. So this bond would be 3rd and this would be 4th. Okay, look at this example. Decide the priority around this carbon. pause the video, take your time. You have 30-40 seconds. So please try and assign the priority. Okay. So first balance each group. So this one is a H, carbon, H, CS3, carbon. So look at the very first atom, bromine, hydrogen, carbon, carbon. So bromine bond first, this would be fourth. Now look at this CS3 and this CHOH. So this carbon and this carbon is supposed to be common. Now look at this carbon is directly bonded to the oxygen and carbon, and between oxygen and carbon, oxygen is high priority, and here all the hydrogens. So this bond would be the second and this one would be the third. Okay. So this is the way you can compare the priority. Now move to E and G. Let's talk about E. E is called antigen. Antigen means anti or opposite. So we can say when two high priority groups are in anti side called as E. For example, so if you compare the priority between bromine and hydrogen, bromine would be the highest, and between nitrogen and carbon, nitrogen has high priority. So both high in anti side, so this one is E. Next is Z, which is called Jusaman, which means together or same side. So Z is like same as cis, and E you can say as trans. But E and G nomenclature, we have to decide the priority by atomic number, but in cis and trans, there is no need to compare with priority. You can just look at the two similar groups in the same side, then cis. If it's in opposite, then trans. So here we can say when two high priority groups are in same side, like this. Between OHH, this one would be 1. Between bromine and nitrogen, bromine 1. So both same side Z. I would like to discuss a point. Cis and trans diastereomer of each other. Diastereomer. In the next slide, we will discuss more about relationships like enantiomer, diastereomer. So this is very like early to say what is diastereomer, but for the note point, I can say cis and trans, they have diastereomer relationship. Now the next thing, we are going to start chiral center, also known as asymmetric carbon or asymmetric center. Generally, carbon is a more famous case, so we can talk generally chiral carbon, asymmetric carbon, stereocenter, something like that, okay? But stereocenter is a different thing. I'll tell you later what is stereocenter. But let's start the chiral center and asymmetric carbon. So we can say here, any carbon can be chiral. Any carbon can be chiral. I will discuss other atoms as well as like chiral nitrogen, chiral phosphorus, but here we are going to talk about chiral carbon. So carbon can be chiral if it is bonded with 4 different groups. For example, here fluorine, chlorine, bromine, and iodine. So this carbon have 4 different things. So this is a chiral carbon. Here we have to figure out which carbon is my chiral. So first you can expand the carbon. So this is CH3. This carbon have 2H. This carbon have 3. And this one is 1. So whenever you have CH3, whenever you have CH2 or carbon double bond or triple bond, then that particular carbon will never be chiral. Why? Because there is a 3 same groups, 2 same groups, and this is double bond and this is triple bond. So any carbon can be chiral when it has 4 different sigma bonds connectivity. So this carbon would not be chiral, this one would not be chiral, this one would not be chiral. Now look at this carbon, the middle, this one. So one group is OH, one group is hydrogen, and the left hand side we have CH3, and the right hand side the entire group CH2, CH3, which is different from the left and the rest. So do not compare like carbon, carbon same, so how it can be chiral, or even you can say if left have CH2, right have CH2, so do not say like this is not chiral. Always look at the entire length. For example, now look at this compound. So this carbon would not be chiral because this is CH3, this is CH2, this is CH2, this is CH, this is CH3, this is CH3. So this one is not chiral, 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 this one as well. Because this carbon have 2 same methyl group. Now you have only the choice this one. H different, OH different. Now look at here, left is CH2, right is CH2. So don't say this one is not chiral. Always look at the entire length. So in the left hand side, we have CH2, CH3, 2 carbon chain, but in the right hand side, we have completely different chain if you compare from the left. So this carbon is a chiral. So simply we can say whenever we have a long, like bulky compound, then always look at the entire length. Now we are going to talk about chiral center in ring. Look at here. This carbon have, all the carbon have 2 hydrogens, so we don't have any chiral center. If you look at this one, CH3, here we have hydrogen. The right side we have CH2. The left side we have CH2. So which is same. So go to the next carbon, CH2, CH2. Again same. Go to the next carbon. This is CH2, which is common for both ends. So we don't have any chiral carbon, so 0. Now the third one, this carbon, methyl, H, CH2, CH2 same, CH2, CH2 same, and this is common for both. And even you can check from this end as well. So we don't have any chiral center, so this is 0. Now the fourth case, so this methyl and hydrogen is different. The right side CH2, the left side CH2. And again, I'm telling you, always look at entire length. So first connectivity is same distance. So do not decide here, move forward. So this is CH and CH3, and this is CH2. This is CH2. So we have a different connectivity. So this carbon is chiral. Same thing you can apply for this carbon, hydrogen different, methyl different. This is CH2, this is CH2. Now this is CH2 and this is CH3. So this one is also chiral. So we have 2 chiral center. So number of stereoisomer. would be equal to 2 to the power small n, where small n is equal to number of chiral center. I said other atom can also be chiral. Look at this phosphorus, or even you can say nitrogen, any one of them. Suppose here we have a methyl, here we have ethyl, and here we have suppose any ring, and here the lone pair. So lone pair is also considered as a different group. So methyl different, this ethyl different, this cyclohexyl ring is different, this lone pair is different. So this nitrogen is a chiral nitrogen. So other atom can also be chiral, but in our syllabus, carbon is the most common one. So I said that number of stereoisomer is 2 to the power n, which is n number of the chiral center. Now there is a term called stereocenter. So stereocenter means the center which is responsible for geometrical isomer plus chiral. So we have done what is geometrical. Geometrical means carbon double bond carbon. Means any double bond which can show geometrical, that could be considered as a stereocenter. For example, suppose we have a question here. My question is, how many stereocenter in this compound have? The first question, how many stereocenter? So look at this double bond. So if you expand this double bond, here we have a hydrogen and here we have a hydrogen. Now carbon have two different connectivity. This carbon also have two different. So this is showing geometrical. And this carbon have here methyl, ethyl, OH, and there is a hydrogen. So this one is a chiral carbon. So we have two stereocenter. Two stereocenter. So if question is like how many stereoisomer, then we could say 2 to the power n. So 2 to the power n means number of stereocenter. So 2 to the power 2, which is 4. So we have 4 stereoisomer. Clear? So stereocenter means geometrical plus chiral or optical. This is also called optical. So whenever you have, any of the compound have double bond which can show geometrical like cis and transform, so you can consider as a stereocenter. And if anyone have a chiral center, then you can also consider that one is a stereocenter. For example, suppose we have this compound. And my question is, how many chiral center? So look at this carbon. OH different, H different, methyl different, an entire length bonded to this is different, so chiral. Now look at this carbon. Methyl here, one hydrogen, these two different. This ring connected carbon is different, and the right side we have OH containing carbon, so which is completely different. Now look at this one. The left side we have a double bond, the right side we have CH2, upper side we have a different kind of chain, and there is a hydrogen. So different, so chiral. Always look at the entire length. We could not compare the chiral center over here because we have a double bond, and we know that chiral center must have 4 different, connectivity. This is CH2. Now look at this one. Hydrogen different. This right hand side is CH2 with the OH in the next carbon. This is the carbon having NH2, and this is CH2. 4 different connectivity, so chiral. And this carbon having OH, chiral. And this one also, chiral. So how many? 1, 2, 3, 4, 5, 6. So we have 6 chiral center. So this is the geometrical and chiral center. In the next video, we are going to deal with R and S configuration and the relationship between the molecule. Thank you so much.